Okay, so today I want to talk about what I would call the easier problems from the practice, the light version. This was used in the North Central North American Regional Contest, and I'm picking up the 5 easy problem from that set. But I would say that probably after the first couple of questions, they are not that easy for people that are complete beginners, but still for people that have done a lot of contests or if you have taken computer science 3620, you probably would have at least seen some of these algorithms that I'm going to talk about. Okay, so the first one that we're going to look at is the zebras and ocelots, and let me just quickly go through the problem statements. The famous study centers to how just two creatures, zebras and ocelots. These magical creatures spend their time in a single tall column, each standing atop on the back of the creature below it. Whenever the bell rings, the ocelot, the lowest in the pile, turns into a zebra, and all zebras below simultaneously turn into ocelot. If there's no ocelot in the pile, when the bell tolls, then nothing happens. Okay. The zookeeper has been watching this interesting process for years. Today, suddenly, he begins to wonder how much longer this can go on. That is, given a pile of zebras or ocelots, how many times may the bell toll before there are no more ocelots? The input consists of the number n from 1 to 60, followed by n lines which are Z or O. These gives the order of the creatures from top to bottom, and then you give a single integer giving the number of times the bell must toll. All right. So it depends on whether you recognize what is going on, but anyways, there are some zebras and there's also lots Z and O. And when a bell rings, it says that you look for the lowest, the bottommost O, and turn that into a Z, and anything below that turns into an O. So in this case, the lowest O is also the lowest animal, so that this turns into Z, and that's it. And the next time, the lowest O is this one, so this becomes a Z, and everybody down there becomes an O, and then you just keep on going. Z, O, Z, O, Z, and so on. And you have up to 60 of these things. And the question is, how many steps does it take before all of them becomes Z? And this will always happen, as you can. So why? Because the lowest O always turn into Z. It's true that there are more O's, but how do I explain this? There are always more. If you look at how many Z's there are, eventually the topmost O will turn into Z, and then once you have a certain number of Z's on the top, those Z's will never change back to an O. Okay, so eventually they all turn into Z. Now, if you try to simulate it one step at a time, this is going to run too long. And basically, what you have to realize, perhaps after a while, is that this is actually just binary numbers. Z and O are conveniently labeled that way because Z is 0 and O is 1. And whenever you move to the next one, it's actually the same as subtracting 1 if you look at this as a binary number where the most significant bit is at the top and the least significant bit at the bottom. So if we write it in a more familiar way like this, if you subtract 1, then it becomes this, which is the next one. You subtract 1 again, this time, when you subtract 1, this is 0 and the least significant bit. So all of those bits turns into 1 by borrowing. And then lowest one bit will become a 0, and then the next one's untouched. So if you recognize that actually all these operations that you're talking about is just -1, -1, and eventually you're going to reach 0, then the number of steps it takes for you to go from the beginning all the way to 0, it's exactly the binary value of this thing. In this case, is 8 plus 4 plus 1, which is 13. So you actually don't need to simulate this at all. All you have to do is figure out the binary value of this thing. And the only slightly tricky part, I guess, is that the number of bits here, they tell you it's up to 60. So you have to be a little bit worried about overflow, but as long as you use the 64-bit integers, so C++, there'll be long, or if you want, in 64, T, I think, then that would be good enough. So what do you do, right? So you have to basically know how to convert from binary, from Z and O to binary. And the idea is basically this. So presumably you already read in N. So let me just erase the whole thing. So you read in N. So you declare that, of course, that's an integer. And then you have long, the value that you're trying to get 0 at the beginning. And then we do what is the standard left to right kind of conversion that you may have, if you have not seen before. We say we read in a character, so character C8, C and C8 like this. And then what we do is we always, before we do anything, take the value and multiply that by 2. And then if C8 is equals to O, which is a 1 bit, then we say val plus plus. And that's it. So what happens is if you have Z, O, Z, Z, O, let's say like this, then at the beginning, the value is 0. When it reaches this part, value is still 0, because 0 times 2 is still 0. When you read this, it'll be 0 plus 1, so it'll be 1. When it reaches this, it will become 2, because I multiply by 2, but I don't add anything. When I read this one, it will become 4. When I read this one, it will become 8, but then I need to add 1, so it'll be 9. And basically the idea is that every time I look at one more digit on the right, it will be whatever I have seen before, and then left shift by 1 position. So let me convert it back to binary like this. Let's say I read this much, and I'm about to read the next bit. So I now have the number 4. To read the next bit, I'm gonna put a 0 here, and by adding a 0 to the right, I'm basically multiplying things by 2. And then, if necessary, if the bit is one bit, then I would add 1 to this. And that's how I do the binary conversion. So essentially, this problem is binary conversion in disguise. And then if you recognize that, then it's not too bad. Of course, if you didn't recognize it and try to simulate it, then this will definitely run too long. Okay, so this is supposedly, I think, the easiest problem in the set in terms of the number of people solving it. But of course, it is not completely trivial, because if you don't see this trick, then you'll probably never solve it. All right. So let me just do not disturb. All right, so let's look at the next problem, racing around the alphabet. Okay, so soccer coach has invented a new fitness game that he thinks will help his players' agility and fitness. The center circle of the soccer pitch has a diameter of 60 feet. He marks 28 evenly spaced points on the circumference of the circle. On the first point, he puts tile tokens called A, and then B, and so on, covering 26 of the 28 points. Then there's a space, and there's on the 27, and the last point is a quotation mark. And then it gives each player a slip of paper containing a aphorism, such as winning isn't everything, it's the only thing, blah, blah, blah. So a player starts outside the circle next to the first letter, and when on Bill's go signal, the player picks up his first disc and then picks up running around the circle, outside the circle, picking up the remaining disc in order to get the corresponding letters in the letters appear in the aphorism. A smart player will take the shortest route, possibly changing direction between consecutive letters of the aphorism. One of the assistant coaches make a note of the player's time, and although Joe, blah, 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 okay. Joe wants you to write a program to estimate the expected time for one smart player to complete each of the aphorisms. Assume for simplicity that the player runs at 15 feet per second between stops for pickups, and that each pickup takes 1 second. All right. So now you have up to 20 cases. Each case consists of basically a line that has the uppercase letters, single quotation marks, spaces, and each one of these phrases will be at least 8 and at most 120 characters inclusive. For each run, you have to give the time. Your answer should be accurate to within 10 to the minus 6 seconds. Okay, so basically what we want to do is to figure how long the distance everybody has to run, and then once you know the distance everybody has to run, then you can use this 15 feet per second to figure out how long it takes to run. Of course, each pickup takes 1 second, so the length of the string, it's automatically going to give 1 second for each character. So whatever you compute plus the length of the string. So assuming that you can easily compute the length of the string, we'll just worry about the other part. All right. So there's a circle, but actually we're not going to worry too much about. Hang on, let me just see what is the size of the circle. The circle is what is it? Diameter of 60 feet. Okay. So diameter 60 feet. So you have a circle. And the diameter is 60 feet. So what is the circumference? Why do you need to know the circumference? Because that's where you run. So you need to know how long it is. Circumference is 60 times pi. And what is pi? There are many ways you can compute it, but one way is to just say double pi equals to the inverse cosine of 1 minus 1. Okay, there are other ways you can compute this, but this is one way. Okay, so you can figure out the circumference. So what we're going to do is we know that between each stop, because there are 28 of these from A, B, all the way up to quotation mark and then space, basically there are 28 stops. So we're going to figure out how many steps you're going to take at each time. And then the number of steps is basically the circumference divided by 28. Okay, so we're going to count steps. So what are we going to do? The first thing is we got to read that string, assuming that you read the first case, the number of cases, and then you just loop to it. And because there's spaces, you have to remember that you need to use getLine. Otherwise, all the spaces will be skipped. So you read it, and then of course, as I said, the answer includes line.length because each pickup of each character needs the 1 second. So whatever answer we compute, you're going to add line.length to it. All right, now, how do we compute this? So what are you going to do is we're going to do for int I equal to 0, I plus 1 less than line.length. Why do I do plus 1? Because I only go to the second last character. I only have to measure. So if I have, I don't know, if this is my sentence, then I only need to know how long it takes for me to go from W to I, how long for me to go to I to N. I don't need to know how long for me to go to N to something else because there's nothing else to go to. So then I have to, let's just call it, so in answer, let's just say segment, how many of these segment I'm doing, and just say segment plus equals to, let me call it distance from line I to line I plus 1. So somehow that is going to tell me from W to I how many of these segments of 28 parts of the circumference, how many of these parts do I have to go from line I to line I plus 1. And then at the end, the answer will be, what is the answer? The answer, so this would be double, would be 60 times pi divided by 28 times the number of segments, okay, and then plus, because we have to remember line dot length, and then you print that out, something like that. So then the main question now is, how do we figure out from one letter to another how long it takes, right? So there are basically kind of two ways you can do this, but the easiest way, it's probably like this. So let me just, so what do I call it? Int distance from C1 to C2. So I would do something like this. First, I need to figure out what is the index of that character. So I would probably do something like this. I'll write a function in, what do I call it? Index C1. So what I call I1 equals to, maybe let me write this better. Int I1 equals the index C1, I2 equals the index C2. That's going to give me a number between 0 to 27, right? So what I want is A goes to 0, B goes to 1, all the way to Z goes to 25, and then space goes to 26, and then the quotation mark, I guess we should do this, is 27. So basically then, whatever the letter is, so I get basically 0, 1, 2, all the way up to 27, I can either go this way, I can go this way, right? So basically what I do is I just say, well, if I go one way, it's I2 minus I1, and if I go the other way, it's I1 minus I2. But of course, I could get negatives and so on. So what I'm going to do, and then also can go over 28. Can I go over 28? I guess I could be, if I'm going this way, I could be doing something of 1 minus 27. If I want to go from 27 to 1. Okay, which way am I doing? So let me, 27 minus 0. Okay, so let's look at this one simple case. I can go to this way or go this way. Okay, so what I'm going to do, this should be just 1. So I'm going to just make sure that I don't get into any trouble with negative numbers by adding 28 mod 28, like this. That will make sure everything is going to be positive. So for example, here, if I2, let's say I2 is 0 and I1 is 27. So I can go, so which way so I'm trying to go from, hang on, let me draw this again. I'm trying to go from 27 to 0. So I can take this way, or I can take the long way. Okay, so of course we know which way is better, but we will just compute this. If we go I2 minus I1, that's the short way. So I2 minus I1 would be negative 27, but 28 would be 1, mod 28 would be 1. So going this way will be 1 based on this formula. And going the other way, I1 minus I2 will be 27. And then 27 plus 28 mod 28 would be 27. So it was 27, right? So basically this will tell me, how, if I go one way versus the other way, whether I go clockwise or counterclockwise. And then I'm going to take the minimum of these two because I want to get the smallest one and just return it. And that will allow me to figure out between any two letters, what is the best way to go from one way to another. Okay. Is there anything else to say? I guess another way to say it is, if you compute whichever way it is, you don't have to do it this way. You can compute one way, whatever way it is, and then the other way is the 28 minus the other way. So whatever this answer gives, 28 minus the other one is the other way. But this is equivalent. Okay. So now the next one, things will start to get a little bit more interesting. So after successful Kickstarter campaign, Steve Arriva has raised enough money for her mail order biology supply company. Steve's amoebas can strategic dishes already populated with a colony of these tiny one-cell organisms. However, Steve needs to be able to verify the number of amoebas her company sends out. For each dish, she has a black and white image that has been pre-processed to show each amoeba as a simple closed loop of black pixels. So a loop is a minimal set of black pixels in which each pixel is adjacent to exactly two other pixels in a set. Adjacent means sharing an edge or corner of a pixel. So in other words, if you are a particular pixel, each of the 8 neighbors is connected. All black pixels in the image belong to the same loop. All pixels in the image belong to some loop. So this means that you don't have some pixels that are just hanging around that you have to somehow discount. Steve would like you to write a program that counts a closed loop in a rectangular array of black and white pixels. No two closed loops in the image touch or overlap, so that's good. One particular nasty species of cannibalistic amoeba is known to surround and engulf its neighbors. There may be amoebas within amoebas. For instance, each of the images below in figure 1 contains 4 amoebas. So there's one loop here, and then there's another one in the middle. This maybe you don't say this is a loop, but it's sort of a triangle. There's another loop here, and then here there are 4 loops. So you're given a 100, at most 100 by 100 grid. They have pound signs or dots, pound being black, dots being white. And for every black pixel, exactly 2 of its 8 neighbors are also black. Okay, that's actually not that important. Then you have to basically count the number of loops. Now, if you've taken 3620, this is a very classic problem with just basically counting connected components. And that's it. Okay. The fact that these are loops is kind of a red herring. It doesn't actually matter at all. Because they tell you that things don't touch and all that stuff. And then every single black pixel belongs to some loop. So you don't even have to care if they're actual loops or not. You just have to care how many things are connected to each other. So there are many different ways you can do connected component analysis, and I'm not going to actually write the code for it. But basically, you can do depth first search, you can do breadth first search, or you can do union find. Any one of those methods will work. Do I want to actually write any code for that? I don't know. Sure. Okay. Well, since this is supposed to be for beginners, let's see. Then maybe I'll write the actual code. So what am I going to do is that in my main program, after I read, let's say I read the grid character, let's call it A, 100 by 100. Let's imagine that I already read it, and they're already in dots and they're already dots and pound sign. Then I'm going to just loop through. Okay, before I do the loop, hang on. And the count is equal to 0. Then for R equal to C, R less than whatever they call it, M and N maybe. I don't remember. So why don't you just look? M and N. Okay, but it's lowercase. So we'll use lowercase. The lowercase. Okay, so now if a RC is empty, then I don't do anything. I just continue. Otherwise, I have something to do. And the way that I'm going to do this is I'm going to call DFS the array and then the coordinate. And what this is going to do is it's going to go and mark all of them. So what I mean by mark, it's going to turn the pound sign into a dot. So clear it up, basically erase the amoeba, and then recursively go and do all the ones that are connected to it. Okay. Why do I do that? Because once I process it, once I see an amoeba, I want to erase the whole thing so that I don't see it again. Why am I indenting this? I shouldn't be indenting this. The DFS A, R, and C. And then I'm just going to say answer plus plus because I have processed one more amoeba. And then at the end, I just print out the answer. So then the question is, how do I write this DFS? So void DFS. I guess I need character A, 100, 1. It's probably better actually to declare this array as 102 by 102 and then just pass the array top, bottom, left, right by a row of dots. So it's easier to figure out, how do I say this? It's easier to avoid going out of bounds when I'm looking for neighbors. But anyway, that's what I have now. So I'll keep it at that. So the first thing is, what I'm only going to call DFS if it's a pound sign. So the first thing I'm going to do is I'm going to clear the pound sign into a dot. Then I'm going to go and look for neighbors. So for in R, let's say R2 is equal to R minus 1. So I'm going to look at all my neighbors. So this looks around the box that I'm in. And now I have to say if, okay, what do I need to do? I need to make sure that I'm not out of bounds. So if 0 is less than or equal to R2 and R2 is less than M. Of course, just assume that M and N are available. I didn't pass it in, so maybe that has to be global variable, so pass it in. C2, so this mixture that I am inbound and AR2, C2 is the pound. Okay, so if the neighbor's inbound and is a pound, then I have to go and recursively erase it. So I'll say DFS R2A, R2C2. And eventually I'll run out of things to erase for this amoeba, and it'll erase everything. Okay, so that's pretty much what you have to do if you want to use DFS. I guess that you can use DFS too, or you can use other things. You can use union find if you know what that is and how to use it. Doesn't really matter. There are many ways you can do this. It's the first standard counting connected component, if you're familiar with that from the introduction to graph algorithm. Okay, so that's the third problem. Now we get to something that maybe is now a little bit more challenging again. Okay, a new town is being planned, and the designers have some very specific ideas about how things should be laid out. First, they lay out the street. Each street is perfectly straight and passes completely from one end of the town to the other. These streets divide the town into regions, and each region is destined to be either residential or commercial. The town planners require that any two regions directly across the street from one another must have different destinations. On this one particular day, all the streets have been planned, but none of the regions have been designated. One town planner wishes to purchase two properties, and it is important to him that the properties eventually have different destinations. For this problem, the streets can be modeled by lines in the plane that extend forever in both directions at no width, and properties may be modeled by points. Given the lines and 2 points, can you decide whether or not they must get different destinations, commercial, residential? Okay, so you have S, which is the number of streets up to 10,000. The next S lines each contain 4 integers, x1, y1, x2, y2, specified coordinates of 2 distinct points, which are the unique lines for the street. So the 2 points gives a line, and this line gives you a street. Each coordinate is in the range from 0 to 10,000, and no two lines will be identical. That is, the town will have S distinct streets. Next line contains T integers, the number of pairs of properties to test, up to 1,000 pairs, and the pairs will be distinct integers, two distinct points, and you want to know if they're in the same or different. Okay, this looks pretty overwhelming if you have never done geometry problem before, but let's just think about what's going on. So you have some kind of a city of some shape. You don't really care, actually. And then you have streets that are specified by 2 points. So maybe you have 2 points here, so that's specified street, and it runs forever. Okay, pretend this is a straight line that I drew. And then you might have another street, and you might have another street, and you might have another street, and then so on. Okay, like this. And then you might be given a point here and a point here, and you're asked, are they the different types of properties? It's residential versus commercial. Okay, so how does this work, right? So if you call this commercial, then the next one that it touches must be residential. This one must be commercial. This one must be residential. This tiny little one here is commercial. Does that work? Yes. And then this one has to be commercial, and this one has to be residential, and then these two are of different destinations, right? But if you say, well, what about this one and this one, then they're the same. So this looks kind of really nasty because you have to take this unknown shape of a city, divide it up into all these regions and try to figure out what all these regions are. So you have different shapes, some are triangles, some are quadrilateral, some who knows what. Right? You can have very strange shapes. You can have, lines like this, and you have pentagons. You can have whatever shape you can think of. Well, actually, there are shapes that you cannot have. But you have to keep track of these regions. You have to keep track of which one touches which one. You have to say, well, if one is commercial, then the one that touches is residential. All of that looks really nasty. And I can tell you that it's actually possible to do all of this with a lot and a lot of bookkeeping and a lot of math, but none of this is necessary. Why? If you have a street, that means that whenever you cross this street, wherever you are, if you're sitting at a certain destination, whether it's residential or commercial, it doesn't matter. If you have to cross the street, you will switch. If you don't have to cross the street, then you don't switch. Okay, so what if there are more streets? There's another street here. Well, of course, when you cross this, you have to switch. But when you're going here, you're not crossing this one now. So what am I trying to tell you? What I'm trying to tell you is that whatever street you have, however complicated it looks, and these are the 2 points, I can look and say, if I want to go from here to here, these 2 streets here are irrelevant because I never have to cross them. But these 4 streets here, I would have to cross them once. So whatever destination I have, when I cross, it's switches. Knowing that I have to cross 4 times to go from where I am to the destination tells me, because the number 4 is even, tells me that I end up with the same destination. And it actually doesn't matter how I walk. I can kind of go around, even if I cross this one, that I said is irrelevant, to get back to where I want, I need to cross it back. So basically, it's irrelevant when I look at this street. Because if I want to get to my destination from the start, I always have to cross this street an even number of times, either 0 or twice or whatever. So streets that are relevant, I have to cross an odd number of times. So all I have to do, basically, is what? I have all these streets here, in whatever way, doesn't matter. And I have 2 particular points that I'm trying to test. All I have to do is draw this straight line and count how many of these streets do I cross. 1, 2, 3, 4. If the answer is even, then it means that they have the same destination. If the answer is odd, then they have different destinations. So the whole thing turns out to be a line intersection test. I just say for each street, intersect the green line, I guess that what do you call it? The line by the 2 properties that you're testing against the street. And if they intersect, then count plus plus. That's the number of streets they intersect. And at the end, you just ask, is count even or odd? If count is even, you say same. If count is odd, you say different. And now, the only thing that's how do you intersect 2 lines? And you can do all the math, and this is infinite lines, as opposed to line segment, which means the math is a little bit different. And you can do all this math that you want, or you can go and say, wait a minute, there is a, where is it? GitHub. Let me do this first. I need this GitHub, not on code library. There's a code library that I give you for the programming contest. And you look at source, there is something called intersect line, intersect infinite line. There's also intersect intersect line, which is for line segment. But here, intersect line is for infinite line. You can read the definition, and basically you just have to give in 2 points. And if you want, you can give in a parameter that says where the intersection is, but you actually don't care in this problem. In this case, you actually don't need doubles, but since this code uses doubles, you might as well just stick to it. And it will return one of 3 numbers. 1 if it intersects at a point, 0 if it doesn't, and -1 if the lines actually overlap each other. So there's an infinite number of intersections, but for this problem, you're told that you cannot have this situation. All the lines are unique. Wait, why is my screen sharing paused? Uh-oh, how long have I not been screen sharing? I don't know. Anyway, I guess I'll have to go watch the video later to see how long have I not been screen sharing. And but the idea is that you use this intersect line function to figure this out, to count the number of times the line defined by the 2 properties intersect the street. Well, is that? But there's a little bit of a problem. Okay, what is the little bit of a problem? The problem is, because we're looking at infinite lines, if there's the street this way, this is going to count as an intersection, because this line expands infinitely. So how do you avoid that? Well, if you have the point of intersection, then you can make sure that the point of intersection is actually within this line segment. How? Well, if you have the line, so if you have the point of intersection called P, and then you have these 2 points, call it P1 and P2, then what you need to do is to check the P dot X is between P1 dot X and P2 dot X, assuming that, well, actually that's not the best thing, because I don't know that P1 dot X is bigger than, it's less than P1 dot X, so I'll just call it min P1 dot X, P2 dot X, it's less than or equal to P dot X, and less than or equal to P1 dot X, the max of them. So you have to make sure that this is true, and of course the same thing for Y. That will make sure that the point of intersection is actually in here and not like this, because you don't want to count those kind of intersections. Okay, so you have to add this and this. Yeah, I hope I shared this before. I'm not quite sure exactly when I somehow accidentally stopped sharing the screen. Okay. Anyway, so this problem is about basically line intersection and counting. Okay, the last one that I want to talk about, this is I guess the 5th easiest problem in this set, called lost map. Okay, somewhere in the mountainous region of the world is a collection of ant villages. Connecting these roads to one another is a series of roads, always running directly between 2 villages and allowing travel in both directions. So immediately you should think about a graph with n nodes with a bunch of edges that are bidirectional, right? Okay. Due to the treacherous landscape, building these roads is expensive, so the minimum number of roads have been constructed such that each village can reach every other village by a sequence of roads. Whenever you see this, whenever you say basically everybody can reach everybody else, but also the minimum number of edges, you know that it's a tree. There are no cycles, because if there's a cycle, then there are two ways you can go around this, and one of those, at least one of the edges, will be unnecessary. Okay. So that's what I would say. It's a tree. So these are the things that you should look for: minimum number of rows, and everything can be reached. That means it's a tree. The whole thing is a tree. Trade between these villages is very important, since not every village has access to the same supply of natural resources. Many villages produce the same resource, however, so it is useful for villages to know their relative distance to other villages so that they can choose trading partners to minimize overall trading costs. Note that the distance between two villages A and B is a sum of the length of the individual roads on the shortest path that connects A and B. Okay. The project has been underway. A project has been underway to compute the distance between every pair of villages. This information has been incorporated in a table along with a map that shows the layout of villages and roads that run between them. You have been assigned the task of distributing table and map to all the villages for the betterment of the regional economy. Unfortunately, not long after you were given the task, a gust of wind blew the map right out of your hand and into the countryside. Despite your best efforts searching for it, you have been unable to locate it. You know that you could visit all the villages and reconstruct the map and then start distributing map and table, but this would take twice as long as the original task, and the villages will be very displeased with you. You wonder if maybe it's possible to construct the map given only the table. Okay, your first line of input will contain the integer n, which is up to 2,500, the number of villages in the region. The next n lines will contain n integers each. The jth integer on the I line is the distance from village I to j. All distances are greater than 0 unless I is equal to j. They're less than 10 to the 7, so it's less than 10 million. And it's guaranteed that the distance from I to j is the same as j to I. For each test case, output n minus 1 lines with two integers u and v on each line, indicating that there's a road connecting the villages u and v in this region, assuming that the villages are number 1 through n. Any solution that outputs the original set of rows will be accepted. All right. So you have a distance table. The problem is some of these distances will indicate that, for example, 1 and 2 is 1 and 2. This is the distance here. So 1 and 2 has distance 1 apparently. 1 and 3 has distance 1. And 1 and 4 has distance 2. And these are the original edges in the tree. You also have 2 and 4, which is distance 3. But you just looking at that, I mean, I guess you know that if you knew that the tree looks like this, then from 2 to 4, you can go from 2 to 1 and 1 to 4, which takes 2 to 1 is 1, distance 1, and 1 to 4 is distance 4, distance 2, that's why you get the 3. But how do you look at these numbers and know whether that's a single edge or whether there's a longer path? That's the problem. So the trick here is, I guess, that if you look at these numbers, if you look at a number, I don't know, 10, if the entry is 10 from, I don't know, 1 to 4, well, you don't know if this is one single edge that is distance 10, or it's a bunch of edges that add up to 10, and 1 going to 4 taking multiple steps. However, if you look at the whole table, and of course you do the zeros, and you see it, let's say you see a 5, and every number in your table is bigger than 5, or actually bigger than or equal to 5. If you know, let's say this is 3 to 2, and you see a 5 here, and there are no numbers that are bigger they're smaller than 5, then for sure this 5 must mean that there's an edge from 2 to 3. That's guaranteed. Because it cannot be the sum of smaller edges. Okay? Now you look at the next smallest number. Let's say there's another number 6. That's the next smallest number, and that's, I don't know, 4 to 3. Well, can this 6 be something else, right? Can this 6 be something plus something to get you to 6? Well, this is the smallest number so far. So the only way that you can reach 4 from 3 is this way, the 6. Why can't it be something else? Okay, so why can't it be something else? Why can't it go from 3 to 2 and then go this way? Because that would require you to add a larger number than 6. Because I told you that there are no bigger, other than this 5, there's no smaller number here. So basically in here, even if, if this is the smallest path, then there's no way that adding this with going from 3 to 2 to 4, or in fact going from 3 to something else and then coming back to 4 would be better, would be an actual X. There's no way this could be the 3 to 4 with the 6 could be a combination of other segments. So this must be a 3X. And then we just keep going. We just keep on looking at the next smallest number, and maybe the next smallest number is this one, and then this is 7. But of course now you realize that, well, 2 to 4, okay, even though the best path may be 7, you know that this has to be some other way. Maybe it cannot be a direct edge because you're told that this was a 3. So there might be some other way to get from 2 to 4 using 7. Because if it's 3, this cannot be, because 2 and 4 was already connected and you create a cycle. So if you have taken 3620, you would probably, you would hopefully by now realize that this is exactly Fresco's MST algorithm. And in fact, that's exactly what you have to do. All you have to do is basically take all these tables, entries, put it into, pretend that these are actual edges of your graph. So if you see 2 to 4, 7, you just draw in your graph and add from 2 to 4 would add weight 7. And you just build this complete graph. You run Fresco's algorithm, and it will just pick out exactly the edges that you need that are that's actually the minimum spanning tree. And if you haven't seen minimum spanning tree of Fresco's algorithm, perhaps that's a little bit harder to know. But if you've seen this concept, even if you haven't seen Fresco's algorithm, if you've seen MST, that's what you need to do. And then if you go to my GitHub repository, the code library, there is some MST algorithm, which is Fresco's algorithm. Okay, implementation of Fresco's minimum spanning tree algorithm. And there's a bunch of stuff involved, but there's a sort of an example code on how to use it. And of course, the example code on how to use it is not what you need, but it's almost the same because this basically comes, this example, if you have a bunch of points in two-dimensional space, the distance is the pairwise distance of every possible pair. Well, you don't have the endpoint and compute all pairs of distance, but you actually were given the table. So instead of doing this calculation, just put in the table entry you compute the MST. This will tell you, the index will tell you which edges are the ones that are chosen, and then just print that, basically. And you can even print it here, every time you chose something. So anyway, this is the minimum spanning tree in disguise. And if you recognize that, and you know that there's code to do that, then that's where you do. Okay, so I guess that's the 5 easy problems. I shouldn't use the word easy because certainly they're not trivial, but they're the easier problems in that sense. All right, I'll stop here.